All right, Andrew, I'm ready. Limits at infinity. We're just going to jump in.
Okay.
Lots to talk about today. All right, example number 1. Notice that we are finding limits at infinity. Okay? We have 5 plus a 1 over x squared. All right? Andrew, we've been talking for a good week now about direct substitution, right? Now, I'll just be formal with you about being informal, right? Direct substitution with infinity is not necessarily like a common practice. Like you would never see in a textbook, like, first of all, that just looks weird. You know what I mean? Like you wouldn't see that.
Yeah.
But there's nothing wrong with you thinking like that, right? Am I going to be upset if you put that on your paper? No. No. Right? But for example, I have seen like BC Calculus, Calc 2 rubrics on the EP exam where if you put infinity, they don't give you a point out of the 9, right?
Yeah.
Which I think is silly,
Right.
but that's just me, okay? So, formally, you don't plug them in, right? You don't, it's not a common thing. But it's still good for you to think about it, right? So for example, we've already talked about this one. When I plug infinity into this, what's 1 over infinity?
No.
What's any number divided by infinity always going to be?
0.
0, right? So what do you think the answer to this thing is?
5.
It's just 5. I mean, it literally is just 5 plus 0, aka 5, right? It's limits at infinity. You cool with that?
Yeah.
Right? It's okay to think about direct substitution there because it makes sense. 1 over infinity is 0, so the answer is just 5 plus 0, 5. Great. Let's do like a 3-parter right here on this one. Andrew, you ready?
Yeah.
Just to kind of like drive a point home. If I wanted you to find the limit at infinity for this expression, okay? I've already given you a refresher course on this one as well, right? You look at that and you're like, Mr. Baker, I could try direct substitution. If I plug in infinity, you get 2 times infinity plus 5, still infinity. Over 3 times infinity plus 1, still infinity. What do you think infinity over infinity is?
0.
I'm hearing some, lots of different answers. Just so you know, we haven't really talked about it yet, but here we are. These are 2 equivalent statements almost. They're not equivalent, but they mean the same thing. What is infinity over infinity actually called? Indeterminate form, right? This is actually indeterminate form, which means we got to do something else, right? Indeterminate form. We got to do something else with that one. But if you have knowledge of rational functions, you really don't have to show a lot of work for this one. You know what I mean?
Yeah.
You look at that one and you're like, wait a second. We can start with the whole process. What's the horizontal asymptote?
3. No.
What did we say when the power on bottom is greater? Horizontal asymptote is an automatic
0.
0. Okay, it's an automatic y equals 0. The reason why the horizontal asymptote is important with these kind of rational functions is because you're really asking yourself, Andrew, what is this graph doing as I go out to infinity? You know what I mean? That's really what this limit expression is asking. What is this graph doing as I go out to infinity? Well, if you really understand rational functions and you understand that, for example, like 1 over x, we know that this graph looks like this, right, Andrew? What is this graph doing as you go out to infinity? Where's this arrow going? To 0. It always goes towards the horizontal asymptote, which in this case is 0 for this one because the power on bottom is greater. So if you look at a rational expression, with integer powers, x squared, just like a polynomial kind of thing, polynomial over polynomial, you can just look at it and be like, what's the horizontal asymptote? What do you think the answer is, Andrew? It's 0. Where is this? Where are we going as we go out to infinity on this graph? It's all about the horizontal asymptote. Okay, it's all about the horizontal asymptote. To drive that point home, we'll do another one real fast. You're going to notice the exact same expression. Andrew, what happens if you saw something like this, right? Again, if you plugged in infinity, it'd be infinity over infinity, indeterminate form. You gotta do something different, approach it in a different way. But you, sorry, that should be an x squared, Andrew, right? But you look at that and you're like, wait a second. I know something here. What do we know about horizontal asymptotes? Yeah, if the powers are the same, it's the ratio of the coefficients. So I know the horizontal asymptote right here is 2/3, you know what I'm saying? Y equals 2/3. Therefore, what do you think the answer to this limit is?
2/3.
It's 2/3. This graph is always going to approach the horizontal asymptote as you go out to infinity or negative infinity. It's going to approach the horizontal asymptote. Wasn't there always three cases though? When the power on bottom is greater, it's an automatic 0. When the powers are the same, it's the ratio of the coefficients. What was that third one?
Slant asymptote.
When the top is greater, right? So what if I had something like this, right? And the top was greater. Andrew, what do you think? No? I'm trying to help you out, right? Like I'm trying to help you out. When we graphed this just a day ago, we had like a slant asymptote, right? We might have had a vertical asymptote, really doesn't matter. But this graph looks something like this the other day, right?
Yeah.
As I go out to positive infinity, where's this graph going? To infinity. So what do you think the answer is? It's infinity. Guys, I can tell you right now, when the power on top is greater, and you're doing limits at infinity, what's your answer? It's infinity. Right? Brady, you cool with that?
I am cool with that.
He's cool with that. Carter, you cool with that? Colin, what about you? You like that? Okay. What happens though when it doesn't look like a normal rational function that I've seen before? Right? Andrew, what do you think?
I'm not sure.
What if I told you your first line of defense is with limits for the last week? Right? I know it's not formally accepted, you know, right? But I just want you to think about it for 1 second. If I plugged in negative infinity, there should be a little laughter in the back of your mind. Coming to mind. Okay, because this is something that she taught in her class. I plugged in negative infinity. Where did negative exponents go? If you have a negative exponent on top, where does it go? It goes to the bottom. If you had a negative exponent on the bottom, it gets moved to the top. You have negative exponent. We'll just splice
There
them
we go.
together. I don't care.
Yeah, it restarted.
Andrew, you ready?
Yeah.
All right. So negative exponents go down to the bottom, right?
Mm-hmm.
So could I rewrite this as 1 over e to the infinity minus 1 over 5 plus 1 over e to the infinity? Right? When they get moved down to the bottom, they actually become positive, right? When you move the negative exponents down, they become positive.
Mm-hmm.
Well, e is already a really big number.
Yeah.
It's an exponential function. And when you do e to the infinity, that's just like huge. You know what I'm saying?
Mhm.
What do you think 1 over infinity is?
It's 0.
It's 0, right? So this essentially goes away. This essentially goes away because 1 over infinity is 0. So what's your answer? What is the limit of this thing as you approach negative infinity? It's negative 1/5. Picking up what I'm putting down here, Andrew?
Yeah.
Okay, good. Colin, what about you? Molly, what do you think? Emily? You like it? Well, you know, you just got to be careful with this kind of stuff because what happens if I just change it to this right here?
Would you just do the same thing and cancel it?
What?
No, I don't think that's right.
Andrew? If I plugged in infinity right now, you get e to the infinity. What do you think e to the infinity is?
Infinity.
So you're gonna get infinity minus 1, which is still infinity. 5 plus infinity is still infinity. You're gonna get infinity over infinity, indeterminate form. Darn. Usually when you get indeterminate form, what's the next thing you gotta do? Some kind of algebra, right? Well, let's learn the algebra technique for limits at infinity. This is the only technique you use for limits at infinity. Do you do it for limits at x equals as x approaches 2?
No.
No. You only do this technique when you have limits at infinity. Okay, so Andrew, I call it the dividing out technique. And you're like, what is that? Okay, the dividing out technique. Here's how I look at it. You look at your rational function here and you're like, all right, what is the highest expression of x? Like, in other words, what expression up here has the biggest power, the biggest punch, right? It's e to the x. E to the x is the highest expression of x. You know, earlier we had like x on top and x squared on the bottom. Which one's the highest expression of x?
X squared.
X squared, right? And I'll come back to that here in just a moment as well, but highest expression of x. So I look at it and it's actually e to the x. Whether it's on top, whether it's on bottom, doesn't matter. Well, whatever it is, the highest expression of x, you're going to divide the top by it, and you're also going to divide the bottom by it. Now, algebraically, I am not changing this in any way. Because you know what I'm really just multiplying by? What is 1 over e to the x divided by 1 over e to the x? It's just 1. I am not changing this in any way. I'm essentially just dividing the top by e to the x, and I'm dividing the bottom by e to the x. Right? I'm really just multiplying that equation by 1, and I'm not changing a darn thing. So Andrew, why do you think we did that? It's going to help us solve the problem.
Yeah.
What do you think I'm going to do from here?
Break it apart.
You're going to break it apart. As soon as I break it apart, what is e to the x over e to the x?
1.
So I'm going to get 1 over e to the x, right?
Yeah.
What do you get when you break it apart on the bottom?
5 plus 1. Or 5 over e to the x plus 1.
Cool, right? You get to that step right there. You're like, ooh, that's cool. That's cool. I like it. Could you try direct substitution right now?
Yeah.
Right? If I plugged in infinity, what's 1 over infinity?
0.
0. What's 5 over infinity?
0.
So what's my answer then if I plugged in infinity right here?
1 over 1.
It's 1 over 1, which is just 1. Woohoo! See what I'm saying, Andrew? Now, Andrew, just to like bring it back here just for 1 second, real fast. Just a second ago, did I have a problem on the board that looked like this right here? And you automatically said the answer was what? It's 2/3, right? Well, it's regular. The powers are the same. It's the ratio of the coefficients. The answer is 2/3. Let's just say for what you had like a brain fart, a huge brain fart, and you're like, I don't remember the thing over there, but I know the dividing out technique. Does it still apply to something like that?
Yes.
Absolutely, right? You look at this and you're like, what's the highest expression of x?
X squared.
It's x squared. Would I divide the top and the bottom by x squared, Andrew? Look what happens when I divide the top and the bottom by the highest expression of x. And then you separate them. What's 2x squared over x squared?
2.
It's just 2. Plus 5 over x squared. What do you get when you separate this? What's 3x squared over x squared?
3.
3. Plus 1 over x squared. What do you get now when you plug in infinity, Andrew?
2 plus 0 over 3 plus 0.
And the final answer would be 2/3, right? The dividing out technique is what you do for limits at infinity, right? If direct substitution doesn't work and you get indeterminate form, you got to do the dividing out technique. Colin, does that make sense?
Yes, sir.
Molly, what do you think? Okay, all right. Let's look at a fun one. Okay? These are always fun, Andrew. It's number 4, I think. Is that number 4? All right, here we go.
Close enough. Okay, cut it. It's okay. Stupid.
Jack, how you doing today?
Good.
Haven't talked to you yet. You doing all right?
I was doing better before.
Oh, no.
Ah, Jack. It's good to see you. You know what I'm saying?
Let me get ready.
That's right. All right, so Jack, what do you think?
Substitution.
Okay, that's good. Jack, if I plugged in infinity, 3 times infinity minus 2 is still infinity. If I plugged in infinity on the bottom, take the square root of it, what do you think the square root of infinity is?
Infinity.
It's still infinity. So you're over here with infinity over infinity, indeterminate form, and you're just like, I gotta do something different, right? Well, what's the only thing that I've taught you to do?
The dividing out technique.
The dividing out technique, right? This isn't like normal rational functions that you've seen before, right? There's been no radicals.
Yeah.
You know what I'm saying? It's always been like polynomials, basically. X squared, x cubed. Anytime you guys have ever looked at rational functions, you never had radicals before. Or like rational exponents. So you look at this and you're like, ooh, a little different. Well, could I do the dividing out technique? Absolutely. Jack, what is the highest expression of x?
Well, I'm inclined to say X.
It is x. Because you have an x on top, and you know what you really have on the bottom?
An X.
Because what does the square root do to that x squared?
Makes it an X.
Makes it an x. So the highest expression is x. Now, if I did the dividing out technique, why am I doing this? Why am I writing the top one like that and the bottom one like this?
I don't know. To make it easier. She was my geometry teacher, so it doesn't really.
Oh, you talk about this in geometry with geometric means?
I don't think I did.
Yeah, you do, man, Jack. I'm telling you. Jack, you do this. Jack, what's the square root of x squared?
X.
It's just x, right? Mr. Baker, why are you writing it like that? Well, it's because I remember my algebra teacher teaching me something along the lines of this. Can you take 2 radicals and combine them into 1?
Yes.
Right? The only way this x squared is going to get to mingle with all this stuff up here is to divide it by the square root of x squared, right? This one has to have a house too, so it can play with the other people inside the house. You know what I mean?
Yes.
Right? That's why I did that. You cool with that?
Yeah.
All right. It's Tidwell. So Jack, if I split these up real fast, what is 3x over x?
3.
Yeah, you just get 3. Mine is 2 over x, right? I'm splitting it up. Because these both have the radical now, you can write it under one house, right? You can write it under just one house. And what's 2x squared over x squared?
2.
It's just 2 plus 1 over x squared?
Yeah.
Yeah? So what's our final answer here once we plug in infinity? 2 over infinity?
0.
0. Good job, Jack. 1 over infinity?
0.
0. What's the final answer?
3 over root 2.
3 over root 2?
Yeah.
That's good. Now, Jack, Mr. Baker's going to go on soapbox for a moment just because he graded a bunch of quizzes yesterday. Okay? What have you done your whole algebra career when you see a radical on the bottom?
Rationalize.
You would rationalize it, right? I told you on the AP exam, do they let you leave radicals in the denominator?
Yes.
Yes, I did. It's unfortunate, right?
Mhm.
It's unfortunate, but I'm just on my soapbox for a moment because if you ever feel like just making Mr. Baker feel warm and fuzzy inside when he's grading a bunch of papers, and you're that beacon of light that wants to rationalize and get off the denominator, make me feel really good about myself. I'm just saying, do you want a happy grader or do you want a frustrated grader?
Probably a happy one.
Yeah, happy one's good. Happy one's good. Andrew, are you going to rationalize?
Yeah.
Actually, Andrew, you probably already know.
His bones are.
Wasn't the rationalizing that was the
I know.
problem.
That's okay though. All right. So we cool with that, Emily? Answer 3 over radical 2. But here's like the big curveball. Andrew, you ready?
Yeah.
What happens if I write something like this now?
Just go for it.
Go for it. Well, if you plugged in negative infinity,
Right.
you're going to get negative infinity on top. technically, when you plug negative infinity on the bottom and square it, you get positive infinity. And you take the square root of it, so you really get negative infinity over positive infinity, which is still indeterminate form, right? Which means you got to do something. But here's the problem you kind of run into, Andrew, right? If I did the dividing out technique, am I not going to end up right back here, where I was just a second ago? Right? If I do the dividing out technique, am I going to end up right here? What do you get when you plug in negative infinity? What's 2 over negative infinity? Still 0. What's 1 over negative infinity squared? Still 0. So what do you think the answer is? Think the answer is.
3 over root 2.
You would think it's 3 over root 2, right?
Yeah.
But you know what the answer actually is?
3 root 2. Oh. No.
It's actually a negative. Okay, it's actually a negative. And let's just talk about a couple of reasons why. This is where they just play around with you. So Andrew, first of all, okay, they do like to do these questions on the multiple choice section.
Okay.
Do they check your work on the multiple choice section? No, right? It's just multiple choice,
Yeah.
right? So if they do something like this, it's on multiple choice. A couple things I just want you to pay attention to, and I just said it just a second ago. When you plugged in negative infinity, what kind of number was on top? A negative number, because negative infinity would be on top. What kind of a number was on the bottom when you plugged in negative infinity?
Positive.
What's a negative divided by positive?
Negative.
You know what I'm saying?
Yeah.
That's where that negative sign actually comes from. Now, some of you might be like, I know what you're thinking. You're like, Mr. Baker, wait a second here. Andrew, what happens if I wrote something on the board like this? And I think it was like, what is it? I don't know. I'm just going off my brain right now. You had an expression like that just a minute ago, right?
Right.
We just did positive infinity, and the answer was 2/3, because that's a rational function that you've been seeing for a couple of years now. Is the answer still 2/3 when you plug in negative infinity?
Yes.
Yeah. Any of those ones, power on bottom is greater. It's an automatic y equals 0. Doesn't matter if you approach positive infinity, negative infinity. It's y equals 0. You know, the answer is 0. If the powers are the same, it's an always 2/3 or whatever it is, going right or going left. Doesn't matter, right?
Yes.
Think about it that way. What do you think the answer would be if the power on top was greater? And you're going left now to negative infinity. Do you think the answer is positive infinity or it's negative infinity?
Yeah.
Which one?
Oh, negative.
It's negative infinity,
Yeah.
right? Because again, of that graph that I just drew, just a minute ago, right? As I go out here, where's this arrow going? Negative infinity kind of thing, right? This is kind of like a big conceptual lesson, Carter. You know what I'm saying? Right? Colin, you cool with that?
Sure.
Okay. All right. Andrew,
Yeah.
I'm just going to mention this for a second because it's like you got to be super careful. Okay, Andrew.
Got it.
Infinity plus 1. I know, thank you. Is the plus 1 really important?
No.
No. Infinity minus 2. Is the minus 2 still really important?
No.
Okay. So really, your brain could see something like that, right?
Yeah.
Which means your brain could really see like the square root of x squared is just, so really your brain could see something like this. I don't know about you, are the powers the same?
Yeah.
What's the answer when the powers are the same?
The
Ratio
Yeah.
of the coefficients. What is the ratio of these coefficients?
3 over root 2.
That's exactly what we just got, right?
Yeah.
However, you could do the same thing down here and still get this, but because it's approaching negative infinity, what's your answer going to be?
Negative.
It's going to be negative, right? The answer will be negative. Just one little shortcut when you're dealing with radicals. Just throwing that out there. Andrew, you got that? Okay. All right, last one. Limits at infinity. Good times. All right, example number 5. Jack! Jack, you do such a great job. Jack, what do you think the answer is?
I don't know. 0.
So you guessed, that's good. Jack, you've heard me say this once today already, and it's good to understand this as a big picture, right? This expression is really asking, what is sine doing as we go where? What is the sine graph doing as you go out to infinity?
Oscillating.
Technically, it is oscillating. It's not really oscillating fast enough to say an automatic D&E kind of thing, right? But you know that this graph, right? You know that this graph is doing this. The whole thing about limits is you have to approach a single value over time, right? Over an infinite amount of time. Is this graph ever approaching a single value?
No.
So what? It's not automatic. What do you think the answer is? D&E does not exist. Right? That one does not exist because as you go out to infinity, are you approaching a singular value, Andrew? No. But what happens when you have something like this? Jack, what do you think the answer is?
0.
I heard a 0. I heard a 1.
1.
People are saying some 1s. I think I maybe know why you're saying 1s, Jack. If you're one of those people out there that are saying 1s. Is that the exact same thing that I wrote on the board the other day, or was this what I wrote on the board the other day? Did I write that on the board the other day?
Yeah.
This is only the special trig case when you approach 0. So that answer is 1. I'm not approaching 0, I'm actually approaching infinity. Well, anybody? Going once? If you plugged in infinity, you would have like D&E over infinity, which is kind of weird.
0.
Jack, let me ask you this. Does sine exist between 1 and negative 1?
Yeah.
Does sine exist between 1 and negative 1?
Yes.
Absolutely. But I don't have sine, I have sine over x. Can I divide everything over here by x if I wanted to?
You could.
And that would turn into negative 1 over x. Mr. Baker, this looks really familiar. What is Mr. Baker doing?
The squeeze theorem.
The squeeze theorem! I picked a function that was bounded. Sine is between 1 and negative 1. I made the expressions look exactly the same. And the squeeze theorem basically said, if you know the limit of the outside, and they're the same, you by golly know the limit of the inside.
0.
So Jack, what is the limit? Jack, what is the limit as I approach infinity of negative 1 over x?
0.
It's 0. What is the limit as I approach infinity of 1 over x?
0.
Well, therefore,
It's
the limit. That's correct, Jack. Thank you.
Is that what I guessed?
That is what you guessed.
That's what I guessed.
It is 0. That's like the beauty of the squeeze theorem right there, Jack. Jack, I don't think it's a full, it's not the best way to think about it. Okay? Saying lots of things in my mind. But could you write it like this? Could you write this like that?
If you wanted to.
Yeah. What does sine only exist in between?
Negative 1.
Okay? If this expression right here is always going to be between negative 1 and 1, what's 1 over infinity again?
0.
What's 0 times any number between negative 1 to 1?
0.
You know what I'm saying? There are a couple different ways to think about that. Sometimes this is really beneficial, sometimes the squeeze theorem is beneficial. Hazel, you got that?
Yeah, kinda.
You have a question?
Well, wait, how does like the 1 over x minus sine x, like how's that the same as sine x over x?
What do you mean? Like this right here?
No, like the sine x over x.
This right here?
How did you like?
Oh, I just split it up because multiplying, you just multiply straight across.
Oh.
So like 1 times sine is sine, right? X times 1 is just x. So I just rewrote it like this.
Okay.
And I know that sine exists between -1 and 1, that's just 1 over x. Right? And if you go to infinity, that's 0. 0 times any number between -1 to 1 is still 0. Is that cool?
Yeah.
All right, Andrew, you cool with that?
Yeah.
Go team.